Do you see
Okay,
the full
now
screen
it's
now?
perfect. It's perfect, yes. You can start.
Okay, great. Okay, so welcome everybody to this course, and thank you for the invitation. Let me move this one here. Okay, so I'm gonna discuss about task offloading. And this is really a short introduction about task offloading, considering the time we have ahead, which is 1 hour. And this is, of course, part of the short course that Professor Billari started discussing about distributed system and cloud computing. Okay, so just a short introduction about myself. So I'm Lorentzo Carnevale. I'm an assistant professor at the University of Messina. I collaborate with the Professor Villeri, so I work on distributed system, but specifically at the cross between distributed systems and artificial intelligence. And I try to create solutions for supporting cities and communities, and mostly for optimizing decentralized self-organized agents. So my research has many applications, smart city, mobility, healthcare, but what I'm going to discuss at the end of the presentation is the application of offloading in TEMA, and TEMA is the European project that we are moving on along with the Thessaloniki University. This is just a short overview of what we will discuss today. So an introduction about the topics, and just a background to understand better what offloading is. The main concept, so the difference between computational task and task offloading, and then all the task offloading objectives. Some application, and the Horizon Europe thema vision that I'm bringing into this course, and then of course the conclusion. About the introduction, so I will not spend too much time on this because Professor Villeri already introduced it, but it's important to understand that we start from the concept of cloud computing, okay? So this system that is able to distribute IoT resources on demand, so when the user will request it via internet, with this concept of the utility computing, so pricing based on the consumption of these resources. We have the free model of distribution, the infrastructure as a service, the platform as a service, and the software as a service, and the colored blocks here in the slide that understand what is virtualized. In the first case, the server. In the second case, server and the operating system. In the third case, the software as a service, everything. So server, operating systems, and application. This is the case of, for example, your client email online, while in the second case is the opportunity provided by some tool deployed into public or private cloud, like would be, for example, Amazon, when provides frameworks for the development, the online development. And the first case is when we try to rent a kind of bare metal, but inside there is a virtualized server that we were going to personalize. Later, I mean, during the time, I mean, cloud computing changed a bit the paradigm to the edge computing. What is the main difference? The main difference is that there was the need to move the computation very close to the data source. The goal is minimizing the latency in transferring data from the source of data to the data centers, so congestion in the network, and this could be a big issue when we talk about big data. And mostly to make the first computation, even if it is a kind of aggregation, so something very small, directly where data are built. Edge computing could be also something not very low power, okay? Low power is mostly for Internet of Things that we will see in a couple of slides, but mostly like very small data centers, sometimes could be also powered by still by battery, but something that is already or a microprocessor or a processor with not a big capacity like it is, of course, a cloud computing. Here there are two visions of edge computing provided by Microsoft Azure and Amazon Web Service, so AWS, the two providers from Microsoft and Amazon of cloud computing, and in this case, edge computing, that more or less they say the same things. Edge computing is very interesting also for artificial intelligence, because this tries to move the execution of AI models from the data centers to the device. What is a device? The device is, for example, a robot. The device could be a drone that is making some computation on the field. The device could be also a kind of small computer that is deployed in an hospital that is present in a rural area. So instead of having to wait for the device to establish an internet connection, this can start processing data on where data are generated. So edge computing is this kind of paradigm that tries to reduce the need of moving a lot of data, and mostly raw data, over the internet. Another important aspect that I didn't mention is the privacy, because not moving data allows to maintain the sensitivity and the privacy of this data that doesn't move from the data source, and then they are not subjected to any kind of attack during the network communication. The other important part of the introduction and the background is the Internet of Things, so the IoT. So the IoT, of course, refers to a network of physical devices. In this case, they are very low power devices that typically are specialized in one single operation. Here we have an example where there is a smart power plug, weather sensor, smart light, and so on. And inside these, we can have microcontrollers. And sometimes this kind of microcontrollers can make some computation a bit more complex. Okay, some microcontroller today is dual core. Some microcontroller has already good capacity for running teeny machine learning models. Why Internet of Things, edge computing, and cloud computing are all important for the concept of offloading? Because they are part of this new computational paradigm that is called computing continuum, or cloud edge IoT computation. In this case, we have the possibility to make the computation in one of the three layers. So the very low layer IoT, the mid layer edge, and the big layer, let's say cloud. And then we have the benefits of running computation in the IoT, the edge, or the cloud. The point here is understanding where to run the computation and according to which kind of metrics, which kind of decision making that could be behind. A definition of the computing continuum provided in this paper, the one that I have here on the bottom, is the paradigm that integrates, organizes, and considers the computing network resources across different infrastructures for deploying workloads instead of relying on specific infrastructure. This is a picture of what computing continuum is. So we have the IoT on the left, the endpoints, the edge in the middle, the cloud on the right. The computing power grows while we move the computation from the endpoints to the cloud, while the device and infrastructure ownership, of course, depends on where the process is deployed. If it is more on the endpoint, is ownership of the user. If it is more on the cloud side, this is the ownership is more in the providers. And we have a repository of resources when we talk about edge and cloud, while we have application when we talk about endpoint. So at the end of the day, what is this offloading? So the task of offloading can be defined as the capacity to transfer resource-intensive application task to an external and much more powerful machine, which is a virtual machine in the case of cloud computing, edge computing mostly, that could be, of course, cloud or edge. So the offloading could be correlated to offloading the whole set of processes that build the application, or just a limited part of it, according to the amount of resources that our computation needs and the amount of latency that our application can introduce. Why we introduce latency? Because when we move a computation from a lower layer, for example, the IoT or the edge, to the cloud, of course, we introduce in the middle the network communication that introduce latency. So task offloading, at the end of the day, is a very complex process that can affect by a number of different factors that we will see during this presentation. Let me now focus on the main concepts and mostly on the discussion and comparison between the computational task and the task offloading. Because generally speaking, we are used to build a computational task. So is what an application is organized with. So an application is composed by one or multiple processes, one or multiple threads, and the most intuitive thing to do is to develop application in a distributed way or in the parallel way when the computation becomes much more complex. A task is identified by one or more operations that can be that produce distinct outputs and can be isolated in a single logical unit. So a task at the end of the day is like a unit of code, or we can just call it a program that can be run in separated environment, runtime environment, or in remote runtime environment. So for example, a program is the most common option for representing tasks, specifically when we talk about scientific computation, when we talk about distributed computing. So in distributed computing, how was discussed before in the previous talk, becomes the running of multiple tasks in different computational machines or in different single logical units that are deployed in different geographical areas. So a computational task is a logic unit of a distributed application that represents distinct operations or program with specific inputs and specific outputs. Typically, we can have one or multiple inputs, but typically the output is only one. It is also a standalone execution. It is very important because if it is standalone, it's something we can decouple from the machine where the task is deployed, is running, and this is propedeutic to create offloading. And this is typically defined by multiple parts. The input data, as we said some minutes ago, but also the output data. But the other important part is the configuration data, because if we think about a DevOps approach, we can separate the executable source code by the configuration data for personalizing this source code. What could be configuration data? Of course, if we think about AI models, the hyperparameters, for example, so different running can turn into different experiments. The experiment can also change because the resources can change. If we run the AI model in an edge environment or in a cloud environment, maybe we can have much more epoch in the cloud environment. And so we can fine-tune these values thanks to the configuration data. This is what we need typically in terms of architecture when we talk about task offloading. So at this point, we change our mind, and we don't talk anymore about computational task, but the opportunity to have the movement of this computational task. Just because we have this definition here in these slides. So in this picture that comes out from the paper mentioned here on the bottom, we have different layers that are typically the layers that I mentioned at the beginning, with the Internet of Things on the left, where we have, in this case, a kind of access layer where the IoT is differentiated by immersive applications like augmented or virtual realities and robotic application. But let's think about a general IoT layer. Then we have the edge layer, where we have different edge sites. Transport, which is the public internet that we will need to use for moving data and computation from the edge of the network and the cloud. And then finally, we have the cloud with the large-scale data center. So the edge infrastructure in this case is a layer in between, like we mentioned it in the computing continuum, between the end devices on the left and the external platform like the cloud on the right. With the edge computing, I mean, we can reduce, of course, as we say, the bandwidth consumption, and we can optimize then the transporting of data and computation to the cloud using the cloud network, of course, and of course reducing also the communication delay. So this is an advantage when we have devices that are battery powered, okay? Because we can increase the lifetime of these devices. Why we can increase? Because communication is one of the most important aspects for energy consumption. So if we reduce the amount of communication, because we reduce the amount of data that are exchanged between the endpoint, the end device, so on the left of the picture, and the cloud on the right of the picture, we can increase the lifetime of these devices. Task offloading has several processes, let me say, and these processes are drawn in the figure here in this slide. And the point is that we can have various hardware components, okay? Because we have not only edge and cloud, but as we saw also in the picture in the previous slide, we have different end devices. IoT application with drones are different from wearable devices or from glasses for virtual reality and so on. So in terms of hardware capacity, of course, we have different amount of resources. We can have, of course, multiple computing processes. This means including also task splitting, okay? So as I say, the task could be composed by multiple operations inside, and we can decide to split the operations for offloading just a part of these operations to another layer. So for example, from the end device, that in this picture is a smartphone, to the target machine that could be in the edge or in the cloud. And then we have the network component, of course, for transferring data between the different hardware components. Still, we have a kind of transferring because we need to transfer the task itself. How we transfer the task? We transfer the task transferring the source code, transferring maybe, if it is needed, the configuration data, and transferring, of course, the input data. So the amount of data that are interested in by this process, so by the task that we're going to offload, of course, needs to be great as well, but not the entire set of data that are generated in the source. Then we have the end device that has a task splitting process, and this decides what is the amount of computation that needs to be splitted, and typically could have a decision maker at this level, or the decision maker can be in the edge on the cloud, to understand what is the destination of this task. The decision can come from really different and variegate factors. Here we have just a limited examples, but in the next slides we will have a better discussion about what is the quality of service requirements, for example, for the application that we are running. Still the battery lifetime of the device. Typical example for IoT devices or in general battery-powered device is that the computation that runs on these devices can be offloaded before to run out of battery. So in this case, the end device has to understand what is the amount of time that remains before to go out of battery, and then taking the task that cannot be successfully computed in the amount of time and then migrated on the target destination. Other kind of factors could be the amount of resources that are needed. For example, the amount of CPU still available in the device, the amount of memory RAM still available in the device, other kind of resources like disk and bandwidth available. So at this point, the tasks may be executed remotely and are transferred using typically a wireless access network when we talk about the Internet of Things, so the end devices. They are typically connected with a wireless access network. And then they move to a remote physical machine that may be much more powerful, and this could be also connected with a wired access network. They are typically executed in the edge and the cloud following appropriate computational approach like virtual machines or some much more lightweight virtualization system like the container. Of course, moving a container, so moving a virtualization, a virtualized process is much more convenient because container is lighter than virtual machine. So moving a container needs less time than moving a virtual machine. The tasks that remains on the device are executed locally using the available computational resource of the end device. So the last step is to recombine the result of both the local computation, so the part of the task that is still running on the local device, and the remote computation, so the part of the task that was offloaded and so running on the edge or the cloud platform. We can have different type of task offloading according to the kind of splitting decision that can be taken. And typically we can derive these three different approaches. So the partial offloading at the edge, the full offloading at the edge, and the partial full offloading at the edge and the cloud. Let's now see them one by one. So when we talk about the partial offloading at the edge, like the name can say, so part of the computation task is processed locally, while the rest is typically offloaded to the edge. Okay, so specifically from the end device to one level up. Partial offloading is typically the most effective approach that can be used by an offloading task, because we can benefit from the local computation and the remote computation. So we can benefit from the resources that are locally available and the resources that are remote available. Because, as I said at the beginning, if we move the entire computation from the end device to the cloud, is like using the traditional approach where we move the entire amount of data and so the entire computation directly into the data center. So increasing the latency, increasing reducing the quality of the privacy of this data. Another level of complexity is when we have to decide which task we have to offload. And typically, an element that is called scheduler is the one interested in understanding what is the target task that needs to be offloaded, and then what is the target layer and the target machine where the task needs to be offloaded. This is very important because inside an end device, we can have multiple tasks, of course, running in a concurrent way, and we need to offload the specific task that cannot respect specific quality of services requirements of this device. When we talk about the full offloading at the edge, in this case, the entire computation that should be run locally in the end device is offloaded and processed at the edge. So this means the full task, so the full set of operations are migrated from the local device to the edge. And so these are fully executed within virtual machines or containers that are deployed in these edge devices. And this becomes a typical resource allocation problem, because we have an entire task that we try to move within a small data center like the edge is. And so we have just to understand what is the virtual machine or container, or what is anyway the typical edge platform that has available resources in order to run the target task. In this case, of course, the energy saving at the end device, so in the IoT, can be maximized, because of course the end device at this point doesn't make any computation. However, we have to dissipate energy in the transmission of data for the computation, configuration data for configuring the application itself, and the source code. And this could, of course, in some way, limiting, the power of the device. Typically, a precise network path from the device to the edge site is required, where the application are offloaded, while still maintaining the quality of experience, the quality of services constraints that are part of the functional and non-functional requirements of the system. Still, we have the partial full offloading at the edge and the cloud. What does it mean? We have a collaboration between the edge and the cloud infrastructure to establish what are the tasks that needs to be offloaded and in which destination. Why this is important? Because edge computing, as I said, is anyway a small data center, but still with limited capacity. So there are specific applications that still cannot run or cannot have fully, cannot run with the full capacity in an edge system, but they need a cloud system. This is the case, for example, of large language models. So there are studies for minimizing the effort of large language models in edge devices, calling them small language models. But still, if the requirement is to use some specific GPU that is a server GPU, of course, this cannot run on an edge device. So in this case, part of the offloading maybe can be on the edge, for example, the preprocessing of data. But part of the task could be on the cloud. So, for example, the training or an inference that can take too much time. Of course, this kind of collaboration has good advantage when we are in a large-scale scenario. We had before the with before the example of the tennis match that was performed yesterday in the Wimbledon tournament. So in this case, when we have a large amount, I mean, in Italy we had 5 million of people in front of the TV and in front of the satellite and streaming. So imagine to have the need to move the streaming close to, I mean, inside the cache server of the provider. So it's possible to move, I mean, part of the computation inside the cloud, so inside the remote platform where the match is provided, but part of the computation could be provided close to the users itself. So according to the geographic location of the servers, I mean, somebody could be closer, somebody more far away, but in this way, part of the computation could be in a kind of edge and part of the computation could be in the cloud. So the main challenge is to have this two-level task offloading decision. So for example, if a partial offloading mechanism is followed, so the first level of decision is in the local device. So this means the local device decides what is the set of tasks that needs to be offloaded to a remote location and the set of tasks that needs still to be run on a local device, okay? Because for the partial we have, I remember, part of the computation in the local device and part of the computation in the remote platform. And so the local device has also to decide if this task could be offloaded in the edge or the cloud, or if the task needs to be offloaded part in the edge and part in the cloud. So this is very complex for an end device, of course, because the end device should have a clear understanding of what happens, I mean, also outside of it, okay? So to understand if the edge or the cloud would be the right target for this device. On the task decided to be offloaded, then we can have a second level of decision. For example, the edge will perform a second task partition, regardless still the offloading, that could be still partial or full, to understand if the edge can run the full set of tasks that are offloaded inside this platform, or still, if the edge is able, according to the amount of resources that are available in that moment, to compute a subset of these offloaded tasks and then executing the remaining part in the cloud. In the later case, so when we have to move data to the cloud, of course, we have to put attention in the transport network, because we need to interconnect the two infrastructures, so the edge platform and the cloud platform, and of course, we will introduce some kind of delay. And the delay, of course, still needs to be inside the quality of service constraints that are imposed by the design of the application. Another point is if the end device is mobile or not, because the discussion we did so far is quite simple. I mean, it's quite linear, and I want to say simple, but it's quite linear if we talk about static devices. Okay, but of course, the end device, mostly if we talk about smartphones, drones, robots, not maybe some IoT that is installed in a farm or the IoT that we have at home. But when we have devices that can move, of course, I mean, one of the most critical component is when it comes the decision of the task offloading, because could be also that when it comes the decision, the internet connection is not fully available, so could be limited, or it's possible that while we are moving, we can target a specific edge platform, but then we move and then we can target another edge platform. So in this case, we have to take into consideration different aspects, okay? And it's very important the time window which spans between the initiating and the finishing of the offloading of the task. Because even the device that moves but starts an offloading is important to understand if in the amount of time that this device moves, we can offloading the amount of operations that we targeted. Okay. So the mobility adds another level of splitting decision. And of course, needs to be decided what is the specific site of edge that should be targeted to offload the computation while the user is moving. What are the cases? Just to make also another example. Autonomous driving, for example. Okay. Autonomous driving, let's take a famous car like the Tesla, make computation, typically makes computation locally. But if something is not doable locally and is needed to offload it in an edge site, the edge site for autonomous vehicles are typical like base stations that are deployed in the border of the street. And while, of course, the car moves, the base station changes according to the position of the car in the street. Okay. And then we need to understand if in the amount of time that intercur between the starting point and the ending point of movement of this car, we can offload the task in one single edge site, or the computation is should be offloaded into different edge sites. Or still, it's important to understand if the amount of operations that we need to offload maybe is too much. So we need to offload a smaller amount of operations. So when we talk about static devices with, or in general with very low mobility, they can, when they are static, so they are stopped, let's say, offloading, of course, they can start the procedure of task offloading. This type of device mobility is considered trivial when we want to study the offloading problem, because we can also think about mobile device that just stop in a position for the time of the time needed to offload in the task, and then start again to move. Okay, so this is a way to simplify the problem of mobile devices while still maintaining the logic of static device. Sometimes this is possible, sometimes of course not. But in this case, I mean, we can try to reduce the complexity of the problem. If the task is static, typically we have two conditions that needs to be met at the same time. One is that the tasks are generated periodically, and the other one is that data size and the CPU cycles requirement of the corresponding tasks in different time will not change. Okay. So if these two conditions are not met simultaneously, then we say that the task is dynamic. Okay, so the task is not static. Then we can have, as I said, devices with high mobility. In this case, the movement affect the network conditions that we have to consider when we offload the task, and the respective resource allocation, because the site, edge or cloud site, could be in some way different. The problem in this case becomes significantly more complex to manage, and typically the computation paradigm that is adopted is called opportunistic computing, that takes advantage of the contact pattern regulated by the mobility according to the fact to determine the amount of computation that needs to be offloaded to other devices. So this means, according to the velocity of this device, according to the distance from the specific edge site, according to the quality of the network, then we can decide to migrate, so to offload one, two, three operations that are part of the tasks, or much more of this. The dynamic task typically arises in two different manners. The first is when the tasks are directly generated during the task generation process. And the second is when the dynamic tasks are derived by intervening the generated statistic task. Typically, it introduces the task splitting and redundancy removing, okay? One of the most important part when we talk about task offloading is understanding what are the metrics, so the objectives that needs to be optimized in terms of having a good offloading. So sometimes could be just the delay, so the latency, for example. Sometimes could be the energy, so according to the fact the device is a battery-powered device. Sometimes could be the bandwidth that that is available. Sometimes just the load balancing, so the amount of resources that are available. Resources, for example, CPU, resources memory, disk input-output, or sometimes just deployment costs in terms of price, because our application is deployed on a server like a cloud solution like Amazon or Microsoft Azure, and of course, with the concept of utility computing, we pay for the amount of resources that we use. Then this could be about the model accuracy, or much more interesting, could be a subset of those or all of those. So this is a multi-objective solution. Let's focus on this, and in particularly in one of those, that is the load balancing, because as University of Messina, in the context of TEMA, we are building some interesting solutions. When we talk about delay, of course, the overall goal is to reduce the total task execution delay. Delay can be broken into different contributors, because delay can come from different sources. The first source is the task execution delay, that comes out by the fact that the task is executed locally at the device or remotely at the edge or at the cloud. In the case we offload the task to the edge or the cloud side, so to remote platforms, we need to take in consideration the transmission and propagation delay of moving all the packets, so the data, the configuration data, and the source code in one of the two infrastructures. And an additional delay contribution could come out from the partitioning of the task. Of course, understanding what is the amount of operations that we need to partition, of course, introduces some kind of delay. The delay objective can be also expressed like the minimization of the average delay or the total delay of the involved task of mobile application. Typically, metrics are response time, there is a type, the delay variation, and the network delay. Then it comes the energy. The energy, I mean, is something quite important today with the problem of climate change and the need to be much similar to a net zero consumption. The reason is that IoT devices are typically battery powered. We need to maximize the lifetime of these devices that are battery powered, and so the device should do the minimum amount of operations in some way. We should understand, I mean, what is the contribution of making computation versus the contribution of transmitting the input data and source code to the edge of the cloud. And typically the metrics that are involved here are the average power consumption or the electricity cost, for example. Let me also add the CO2. So the CO2 equivalent could be also something interesting in this case. Then bandwidth. Bandwidth is quite linear also, like way to think, because we have an amount of bandwidth that our access network can provide us. So we need to maximize the throughput of the application or the utilization spectrum of the device, of course. Load balancing, as I said, is quite interesting because it's a matter of allocation and scheduling of tasks according to available resources of this physical hardware. It's something we have to take into consideration when we talk about task splitting and, of course, task offloading. The goal could be a scalability problem. For example, increasing the resource availability, increasing the number of offloaded tasks currently deployed at the edge of the cloud, maximizing the resource sharing and fairness among multiple users, and facilitating, of course, the offloading of future tasks. The objective can be translated into minimization problem. For example, the minimization of the average percentage of the computational and communicational resource utilization, the minimization of the maximum amount of resource used by the infrastructure, or minimizing the variance of resource utilization. In this concept, we have an accepted and also discussed paper in a conference that was running in May in Norway. So the paper is still not published. That's why there is no the bibliography on the bottom. But we try to focus on the CPU. Okay, try to understand if we can predict the amount of CPU that is used in the future. We started creating an AI model. This AI model is trained over a real case data set. This comes out from the Microsoft Azure Cloud Virtual Machine. We have then multiple virtual machine utilization that are sampled every 5 minutes for 30 consecutive days. There is really a lot of data. We have more or less 100 million of hours and almost 2 billion of readings, so really a lot. The services that are deployed in the virtual machine are first parties application. So this means application provided by employers of Microsoft, sorry. So to build internal services, to build testing services, development of research, but also third parties ones that are the customer services, for example, web service and e-commerce. Of course, for privacy reasoning, we don't know what are the concrete applications that are running inside, but given that they are cloud solution, we expect they are in some way web applications. The virtual machines are of two types, infrastructure as a service and platform as a service. And typically the amount of virtual core is a few virtual cores, 2, 3, 4, something like this, and then no more than 4 GB of RAM. We built two different models. One was not very, didn't provide good result, let me say, that is this LSTM model. And another one that is still an LSTM, but a bidirectional one with attention. In this case, it's a simple model. As you can see, there are not so much parameters inside. And we have results that, according to the normal metrics, the mean squared error, absolute error, and the root mean squared error, it seems quite fine. We have different input window. For a time series application, we need to fix input window in terms of steps, and we predict one single step in the future. Why one single step? Because predicting multiple steps can introduce errors to the second, the third, the fourth, so the future steps, is if the first one has already errors. So we wanted to avoid to eradicate this error. And the other reason is that one step is 5 minutes. Typically, we can have we have enough time to migrate a virtual machine in 5 minutes if this is needed. When we talk about the input window of 2 steps, this means 5 plus 5 minutes, so a total of 10 minutes. 6 steps is half an hour, 1 hour, 2 hours, and so on. So as I say, the metrics seems quite good, but if you see about the prediction, this is not very, it's not like this. So the model is able to capture the average value of the maximum CPU that was used, but doesn't capture the peaks. Okay. Then we try to complicate a bit the model, to increase the amount of parameters, and to add also an attention layer. In this case, the computation needed much more time, so we removed the 96 steps. We have still 1 step in the future. The values are quite good. Their squared is something that starts from a negative point, but is able to move to more or less 50, so to some value that was already okay. Something that I didn't mention is that this kind of application is trained using the federated learning paradigm, so a distributed learning approach where we don't move data from the data source. So we wanted to introduce also some privacy preserving stuff in this scenario. And we used 6 virtual machines, so with 6 different clients. If something that I'm discussing, I mean, is not clear, maybe we can have a short discussion while I finish. I mean, there is not so much slide until the end of the discussion. So then, as I said, the amount of the values of this metric is quite good. And if we look about the prediction, we can say that yes, there are still cases where the prediction is in the average, like in the bottom right part of this slide. But there are much more cases when the peaks are reached. So this is something that we discussed, as I said, in the conference that was in May. But we're already running other models based on transformers that are giving better results than the one I just shown now. But the results are not ready to be shown. The other important point is the deployment cost. So deployment cost is the one that we have to consider when we want to offload the task mostly into the edge, the cloud platforms that are rented by the user. And of course, we need to take into consideration the monetary cost for the computing processing. So for example, the amount of money for CPU hours that are needed, or the memory for gigabyte that is needed, or still the network bandwidth for throughput per day that is needed. So including also network resources and so on. Applications of the offloading. Something that I already mentioned is, for example, the autonomous vehicles. So the key objective here is to reduce the latency and the transmission cost and increasing the efficiency of traffic management. The edge computing is considered in this case as a key technology in connected vehicles, okay, where we have to take care about the geo-distributed services of these base stations and edge devices on the roadside. The idea is typically to analyze data from proximate vehicles roadside sensors and broadcast to drivers with a very low latency. The task may involve the route planning for vehicles, traffic flow prediction, or accident detection, for example. Another application is robotic. Robotic has a great present and a big future when we talk about cloud and edge robotics. Many offloading opportunities are present in robotics. For example, the SLAM, the simultaneous location and mapping, or the planning algorithms that are used for robot manipulation, mobile robots, or any kind of learning task that we can run in a robot. And the other one is, of course, the Internet of Things. So the impact of task offloading can be maximized, and of course, in the context of IoT application, because we want to maximize to minimize, the amount of battery power that we use, and maximize, the available resources. So typically, only small tasks can be executed locally, because IoT devices are generally microcontrollers with very low power capacity. And then the offloading in this scenario focus on reducing the task execution time, okay, response time, and energy consumption. Let me finally give you the vision of the Horizon Europe TEMA project in terms of offloading. It's something that includes, the solution that we've shown before. And in the next slides, I will show you, first of all, what is TEMA, and then second, the design that we want to put inside TEMA. And part of it is already built. So first of all, TEMA. What is TEMA? It's the trusted, extremely precise mapping and prediction for emergency management platform. Is an Horizon Cluster 4 project, this area. This is about the importance of managing natural disasters, because climate change, as you know, is having a big impact in our life, and the number of natural disasters is increasing year by year. First responders needs to have modern and innovative tools to face the issue of managing the natural disasters, not only during the natural disaster, but also before, for the prevention, and also later for planning, for understanding what was good or not in the management, but also for planning future actions. In the TEMA platform, we have a compute continuum solution that is able to run artificial intelligence models, but also interesting virtual reality applications that the first responders, so firefighters, civil protections, Red Cross, and everything, can use in order to improve the quality of the work in this case. While offloading here could be interesting to make smooth the process of computation within the compute continuum that we deployed. This means that on the edge we can have specific devices like drones that can make sampling. We can have some small computers that can start to make some computation. We can have the first kind of visualization system on the edge, and the edge is not powerful to do the entire computation. And then we need sometimes to offload this computation to the cloud, because in the cloud there is much more power, but also in the cloud, that could be the remote location where a control room is located. There are other people, and these other people can try to have a bigger look on the situation. Why we start computing on the edge and not in the cloud? Because, as I said, it's important for the latency. So it's important to give to the first responder a tool and a response in a very short time, and mostly because a natural disaster can destroy the communication system, can destroy antennas, can destroy cables. So it's not so easy to communicate with the remote control. The alternative is using a mobile network or satellite network that anyway is not fast as the normal internet that we use. How can we deal with the problem of offloading in the Tema platform? But let me say that this kind of design is in some way usable also in different scenarios. First of all, we need to monitor the resources. What are the resources? Is the CPU of the devices we have in the edge, the memory, the disk input output, the network, the energy, or a subset of it, of course. For a specific prototype, we don't need to use all of them. We gather resource samples and we send these resource samples through a message queue to specific AI models. We call it AI brain. That still can be deployed on the edge. This is the first challenge, because this means we need to create AI models that are very small, so teeny models that can be deployed on edge devices. In this case, we have resource forecasting, and we had an example in the load balancing matrix, where we already started to work on CPU. And then we have anomaly detection, because we need to understand, according to the future forecasting of computational resources, what will be the behavior of these resources. And then if there will be an anomaly in the usage of these resources. An anomaly means that the CPU is uses too much CPU, or is used too much memory, or is used much more bandwidth than needed, okay? And this anomaly detection can generate an alarm message that then is managed by the scheduler, and the scheduler decides what is the task, decides the task split in part, and decides what is the target for the offloading, that in our case could be another edge device because of the internet connection issue that I said before, or the cloud, and this is done by the scheduler. Just to give you some insight about what are the technologies that we can put in the field. For resource monitoring, could be Prometheus and Grafana. We typically have containers. Prometheus is a famous tool that is able to catch data from CPU, memory, disk, network, and so on, data from the containers to collect, and Grafana to have some dashboard and nice visualization. The message queue could be Apache Kafka, could be RabbitMQ, could be MQTT, could be different of it with different characteristics, but in this case, I prefer to adopt Apache Kafka. Then about the resource forecasting, anomaly detection, and scheduler, the idea is to create something custom. Why? Because the state of the art on offloading and this kind of tasks is, yes, quite wide, but there are not still concrete solutions. So solutions that are not only prototypes or something built in laboratory, and of course we want to build something that could be in some way tailored on the use case, so natural disaster management. So the idea is to create custom models that we can put here. And we already started to work on resource forecasting. We don't have only CPU, but we're working also on CPU and memory. We are not working only in virtual machine, but also virtual machine and containers, in order to target the computing continuum and to target multiple resources. Custom anomaly detection, we started working also about it, both with federated learning or traditional approaches like isolation forest. And then also custom scheduler. I mean, we are trying to work also in this direction, mostly in reinforcement learning or genetic algorithms. This is the most present solution in the state of the art. Okay, let's go to the conclusion. I mean, it's something very simple. I mean, offloading, as you can see also from this slide, it's something that is really a research topic. So I was also curious to go on Amazon before to run the the presentation and to write a task offloading. And yeah, there are no books that we can take to understand what offloading is. So offloading today, it's something that we can study from the scientific community. We can study from papers and other kind of solutions similar to this. Offloading, anyway, is a challenge. It's still a running challenge in distributed systems, and it was born along with the concept of computing continuum, so something that is here was born no more than 10 years ago, something like this. Artificial intelligence could be an important key-enabled driver to provide offloading, because as you have seen, many problems are optimization problems. And typically AI is good for optimization with all the gradient descent approach that the neural network has, but also the standard machine learning solutions, but also the bio-inspired one with the genetics, swarm intelligence, and so on. So AI could be a very important part of offloading. And in some way, this is also part of something bigger that I didn't mention to do not complicate too much the discussion, but this is a way the DevOps, or declined today in something different, which is the AI operations. So it's the artificial intelligence that tries to define what are the correct operations to make a system, a clouded system running in the right way.